Okay. So you're going to practice French, yeah?
No.
Yeah. Ok, bonjour tout le monde. Donc, j'ai le privilège de présider le jury de thèse de Mathilde JAY, qui va nous présenter ses travaux sur l'impact environnemental de la phase d'apprentissage dans les modèles d'IA. Alors, cette thèse était dirigée par Denis Priscrin, professeur à la Grenoble UMP, et Laurent Lefebvre, donc, chercheur à l'ENS Lyon. Alors, la thèse a été rapportée par Aurélie Bugeaud, qui est là. Voilà, donc professeur à l'Université de Bordeaux, et Anne-Laure Ligoza, qui est avec nous, donc professeur à l'Université de Paris-Saclay. Alors, dans le jury, nous avons également des examinateurs et examinatrices, donc Emma Strubel, donc, qui est assistante professeur à Carnegie Mellon University. Il y a également Claude Lepape, qui est avec nous, voilà, donc ingénieur de recherche à Schneider Electric, et Sylvain Bourret, qui est également avec nous, qui émet des conférences à Grenoble UMP ENSIMAG. Et nous avons un invité qui malheureusement n'a pas pu le faire aujourd'hui, donc Paul Monet, ingénieur à Hewlett Packard Enterprise, donc ne sera pas avec nous aujourd'hui. Alors, on va pouvoir commencer, donc 45 minutes exposées. Donc, à toi la parole.
Merci. Hey. I would like to start by thanking everyone who made the journey to come watch my presentation. So today I will present my PhD thesis on a versatile methodology for assessing the electricity consumption and environmental footprint. Sorry. And environmental footprint of machine learning training from supercomputers to edge devices. Okay. So before going further, I would like to spend a few seconds on this quite long title. So the main focus of my PhD is the training of machine learning models. And I do so by studying the electricity consumption, by measuring the power consumed by the computing node performing the training. And I infer the environmental footprint using estimation from environmental databases. During those 3 years, I got to experiment with two computing nodes, namely a supercomputer and an edge device. And since those infrastructures can be said to be representative of today's AI computing nodes, I inferred from my research a methodology that can be applied on most use cases. So I will start by giving a few elements of context before giving an overview of the methodology that I proposed and presenting the infrastructures that I worked on. I will present how I applied this methodology on 6 machine learning models and how I was able to compare a supercomputer and an edge device. I will finish by showing the limits of my approach and how I was able to overcome some of them. Finally conclude. So to start with some context, information and communication technology represent around 4% of the worldwide greenhouse gas emissions. And what's more important is that those emissions are increasing when the IPCC has shown that we need to drastically reduce our emissions if we want to reduce avoid the worst consequences of climate change by limiting warming to 1.5 degrees Celsius. But more than climate change, ICTs can contribute to freshwater change, bare metal depletion, and primary energy consumption. And all those factors can impact the well-being of the planet. In response to those facts, there has been treaties and regulation aiming at reducing emissions. The most famous one might be the Paris Agreement that was signed in 2015, whose goal is to limit warming to 1.5 degrees Celsius. The European Green Deal is a set of directives whose aim is to reach carbon neutral for the European Union by 2050. And it includes a directive that forces companies to report their carbon emissions, and a set of directives who set a limit, a minimum limit in the energy efficiency of buildings, and for example, of data centers. And it means that there is a growing need for the companies to assess the footprint of their digital services, and on the other side, for policymakers to make assessment standards. And if we look at machine learning, so artificial intelligence corresponds to techniques that can handle tasks that typically require human intelligence. Machine learning are AIs that automatically learn from a set of data, and deep learning are machine learning techniques that relies on deep neural network models. And those models that can be characterized by those three parameters, so the model size or in number of parameters, the training data set size, and the number of computations that are required to do the training. And you can see that since the beginning of machine learning, those three parameters, those three characteristics have been exponentially increasing. And if we take one example, Stable Diffusion is a deep learning model that can generate images from text. It has 10 to the power 9 parameters, 10 to the power 8 data points, and it required 10 to the power 22 floating point operation to be trained. And to do so, they used 256 800 GPUs for 25 days. GPUs being graphic processing units that are the specialized hardware for AI. And all of this, it results in a significant impact. And in fact, the International Energy Agency has stated that machine learning is one of the main drivers of increase of the electricity demand in the European Union in the coming year. And they did so by looking at the number of GPUs that were sold by NVIDIA. And they estimated that in 2026, the dedicated AI data centers will consume around 100 terawatts per hour. And so it means that there is a need for the companies to assess the footprint of their machine learning services. And it can be quite complex. First, machine learning services rely on ever more powerful and more specialized hardware that constitutes supercomputers placed in HPC or high performance computing data centers. And for those services to be accessed by users, they rely on networks and then end user services and end user devices. Sorry. And this is important to take into account because several studies, maybe three, have shown that each category, user devices, data centers, and networks, represent a significant share of the global greenhouse gas emissions. So they don't agree on the total value of emissions, but they agree that each category is significant. And in the recent year, there has been a shift of computation from supercomputers toward the users in what we could call edge data centers to reduce latency and traffic. And more than that, today there are accelerators in end user devices. And the question of which scenario consumes less electricity and has a lower environmental impact is still open. But to account for the globality of the impact of machine learning service, we need to take into account all phases. So from the data collection to the processing of data and the selection of model, its training, and finally to its deployment. And each of those phases, they rely on maybe dedicated or specialized hardware that all have an embodied impact as well as of an operational impact. So the embodied impact stands for the extraction of resources, manufacturing, transport, and end of life. So for this presentation, we will use the CapEx name for those impacts and the OpEx name for the operational impacts. And all of that, it constitutes the scope 1 of the impact of the service that are due to the machine learning itself. But there are other scopes. The scope 2 includes the indirect impacts that are due to its applications. For example, if we are building a model that reduces the energy consumption of a building, that would account for the indirect impact. And finally, the systemic impact that evaluates, for example, the change in behavior of user due to this machine learning. And all of this, it leads to the following resource questions. How can we accurately report the impact of machine learning services? How can those impacts be reduced? And can decentralizing the computation reduce those impacts? And so in my PhD, I worked on designing a methodology to assess the impact of training a machine learning model. I showed versatility by applying it on various models and infrastructures. And in doing so, I provide a better understanding of the impact of machine learning training infrastructures. And I am able to compare a supercomputer and an edge node on local training. So if we start with the methodology. So even though the impact of the interest in the impact of machine learning service mainly goes back to the work of Emma Strubel in 2019. My work builds upon studies that I have tentatively grouped here. I evaluate them on the impact indicators, the hardware lifecycle, the scope of the ML system, and the machine learning lifecycle phases that they estimate. And the green lines show the categories that were checked by every study. So we can see that the research has been focusing on the electricity consumption and carbon emissions of the operational phase of supercomputers during the training phase. But in the most recent years, there has been work on the impact of federated learning and machine at the edge, on the impact of the embodied phase, and on machine learning deployment. And the methodology that I present today, it simultaneously adds new impact indicators, more hardware lifecycle on both supercomputer and edge devices on the training phase. And I will show at the end of my presentation how this methodology can be extended to machine learning deployment. So to build my methodology, I based my work on the lifecycle assessment standard, that is the technique for assessing the environmental impacts of a product or service over all of its lifecycle phases. And its most important goals are to permit comparison between projects. It is based on ISO standards and standards from the International Telecommunication Union, and it has the advantages of being multi-criteria and multi-phases. And so what we did is we applied a kind of LCA that is called attributional to machine learning training. And the first step of this technique is to define the scope. So far as we focus on training, on the machine learning compute node that performs the training, and both of their life cycle phases. We only account for scope 1 impacts. The second step for LCA is to define a functional unit. A functional unit is quantified performance that can be used as a reference. So here it's going to be training the model on a given data set until the quality target is reached. And you can see that it's completely agnostic from the infrastructure that is behind, so we can fairly compare them. And finally, we need to select the impacts that we want to evaluate. And LCA recommends to select impacts that are the most relevant for the service. And so for us, it's going to be primary energy. That includes all the energy sources over all its life cycle phases. So for example, for the usage operational phase, The energy is mainly coming from the electricity that is generated by different energy source. So global warming potential evaluates the contribution to climate change, and abiotic depletion potential represent the increase in scarcity of mineral and metals. To assess the impact of training, I separate the operational phase from the embedded phase. For the operational phase, we base our analysis on power measurements of each component in the machine learning compute node with a frequency high enough to capture evolution, using software-based parameters and electricity impact factors to convert the power into impacts. For the embedded phase, we estimate the impact of each component of the computing node using databases, and we allocate them to the training by a time-based allocation. We made sure that our methodology could be used by anyone by ensuring its reproducibility. For the operational phase, we repeat our experiments and we fix and control the environment. For the embedded phase, we made sure to use only public databases. So during my PhD, I have included two computing nodes in my analysis. The first one is an HPC platform, so a node from the Champollion cluster, which was ranked in the top 500 supercomputers in the world, and the edge node is an NVIDIA Jetson AGX Xavier that was designed by NVIDIA for edge use cases. And they are both relevant for the study because they were designed for machine learning workloads. They're quite recent and they have relevant properties in terms of energy. So the Champollion cluster was ranked 22 in the top in the green 500 that ranks supercomputers on their energy efficiency, and the Jetson was designed to be low power. And despite their size, they also have other significant differences. For example, in terms of performances, Apollo is over two orders of magnitude more performant than the Jetson in terms of number of operations per second. And it is explained by the fact that it has 8 GPUs and 2 CPUs when the Jetson only has 1. Regarding the memory, Apollo has 1 terabyte available when Jetson only has 32. And if we look at the energy, so the TDP stands for thermal design power, which represents the maximal amount of power that a computing chip can consume. So Apollo consumes around 4,000 watts, and the Jetson only consumes 30. So if we combine those two metrics into energy efficiency, they are not so far away, but we expect Apollo to have a slight advantage. To measure the electricity, there are several ways to do it. We can have a power meter that measures the total consumption of the node. The power meter can be outside or inside of the node, but there are other solutions. Computing nodes have processor power management library that evaluates the power consumed. For GPUs, it's named NVIDIA Management Library, and for CPUs and RAM, it's running average power limits or RAPO. And we access them using power-based parameters that were proven to be accurate and are available on most nodes. But the question here is which one is better for our use case, and how well do they relate to the power consumption of the whole node, which is what we want to do if what we want is to report the exact energy spent by training. So it was at the beginning of my PhD, and what I did is I started to compare software-based parameters and evaluating them against external parameters. So here you can see the power profiles of 3 parameters on 3 classic HPC benchmarks. So you can say there is a significant difference between the 3. A significant difference. And I completed this comparison with a qualitative one, so evaluating the quality of the documentation, the easiness of use, for example. And I've found that none of those were suitable for our use case because of a lack of configurability, for example, of the frequency for nodes with GPUs, and of versatility, because what I wanted is to be able to measure both my infrastructures, the power of both my infrastructures. And I did this with a fellow PhD student, and we were able to publish this comparison together. And we were quite happy to receive open research and reusable research objects for this work. But that still left us with no way of measuring power that was suitable for our use case. And I was lucky to be reaching this point of my PhD at the time when another PhD student was building a tool for his company. So I asked him if we could work together and include the features that we're interested in. So in the end, Alumet reports time series of GPU's consumption as well as CPU RAM. It enables the configuration of the acquisition frequency, and it is adaptive to edge and HPC architectures. So the tool was open source and is available on GitHub. For the embedded impact, we relied on the work of an association that is called Boa Vista, whose goal is to provide solutions to help companies evaluate the environmental impact of digital infrastructures. And in particular, they have built a tool that's called Data Vista API that provides multi indicators. So basically the one that I presented earlier for multi-phases of the infrastructure. So it includes the extraction of resources, manufacturing, distribution, but not the end of life. And so they did that by aggregating data from various databases, the Adam Carbon database, manufacturer project carbon footprint, and semiconductor LCAs. Sadly, there is no study for GPU, so we estimate them based on the die size, the printed circuit board area, and the memory density and capacity. So we were able to estimate the embodied impacts for the Jetson and Apollo, and found that without surprise, Apollo required much more resources to be created. So the question is, which one is better for training? But just one point before going further, this methodology enables a comparison of the impact of each computing chip, each component in the computing chip. And it's interesting to notice that memory dominates the embodied impact. So here you can see for each impact, the amount, the share of each component in the total impact. And in blue, in particular, you have the RAM, and in green, the GPU chips. So, from machine learning models, we relied on the MLPerf benchmark. That is a state-of-the-art model benchmark suite, whose goal is to compare the most recent computing nodes for machine learning and provide consistent measurement of speed. And you can see that each benchmark is defined by the same characteristic that I used to define the functional unit, which is train the model on a given dataset until quality target is reached. So here we have 6 functional units on which we can compare both our infrastructures. For the Apollo, the code was provided by MLPerf, and it was already adapted by HPE for Champollion. So I could focus on implementing, adding adding element to the implementation and performing the experiment. For JSON, it was much more complicated because we had to install the software development kit, and we quickly realized that it was not compatible with the code provided by MLPerf. Yeah, and we had to start from scratch, writing the code to download the data sets, process it, and train it. And more than that, we had memory limitation and long execution made the hyperparameter search and the testing more difficult. So for those reasons, we chose to focus on ResNet 50. I chose not to present all the results in this presentation, instead focusing on the main messages. So the first one is that power profile can vary significantly. So here you can see the power profiles of training 4 of the 6 models by Apollo. So the power profile corresponds to the power consumed by the 8 GPUs and the 2 CPUs, as measured by NVML and RAPO. And you can see the execution is quite constant, but the value of the power consumed depends on the model. So for ResNet and RNN, it almost reaches the TDP that represents the maximum consumption of the computing chips. But for the LLM, it's around 50% of the maximum power. So if we look at the power profile for the Jetson, it's quite similar in the sense that the power is constant. But for Jetson, we have an additional value that is the total consumption of the node. And we can see that it is above the TDP that was provided by the manufacturer, which leads to think that those values might be unreliable. The other thing to notice here is that the training required 4 days, when for the Apollo it was around half an hour. But maybe the most important result that I got is that most energy can be spent on the very last percent, very last accuracy points. So those graphs represent the energy required to reach each accuracy point. So if you look at the left graph, you can see that to go from 0.75 to 0.8 requires most of the energy. It's not the case for all the models, but for a lot of them. So now if we go on to the embodied phase, if we want to account for the total impact of training the function of the functional unit, we first have to attribute the total impact of the node, embodied impact of the node to the training. And we do so by multiplying it by the fraction of the active lifetime of the node during which it was used for training. And we add that to the impact of electricity that is calculated by multiplying the energy consumption that we measure by electricity impact factors. And as a result, we can see here for Jetson, for training ResNet on the Jetson, most of the average depletion potential comes from the embodied phase, as expected, and most of the primary energy comes from the usage phase. But for the global warming potential, the impact is shared between both phases. So the time has come for me to reveal which computing nodes consume more resources on the training. So looking at the energy accuracy trade-off provides a first comparison, and you can see that Jetson requires more energy to reach each accuracy point even from the start, and is not even able to achieve the quality targets. So what we did is we defined it an alternative functional unit, ResNet 50 star, whose target as accuracy corresponds to the maximum one reached by Jetson, as you can see now on the graph. And to better compare the infrastructure, I built this fader chart, and each metric were normalized so that the goal is to maximize the metric. So for example, what we want is to reduce the electricity consumption, so I converted that into electricity efficiency. So we can see here that Apollo is outperforming the Jackson in all the performance and environmental criteria, and most especially on the speed and ADP efficiency. I thought it was also interesting to compare the ResNet 50 and ResNet 50 star functional units, and you can see how the accuracy can be a good lever to reduce the energy efficiency, because there are a significant difference between both functional units. But I think it was inherently unfair to compare the Apollo and Jetson on only those criteria, because the Jetson was designed for the edge and its associated constraints. For example, its price and the latency of the network. So I tried to add additional criteria here, giving some advantage to the Jetson. But I think that those criteria really depend on the use case and how we evaluate them too. And if we look at this from another angle, we can also say that edge computing can be an opportunity for constraining the computation and force developers to use maybe smaller models. So to summarize, I showed that we can evaluate both the operational and embodied impacts on most infrastructures. And I relied only on open databases and open source measuring tools. And the code that I used is available and reusable. I have shown that the power profile, the accuracy power trade-off, and details of component embodied footprint provide a better understanding and the possibility to find actionable reduction rates. And finally, I have shown that my methodology enables a fair comparison between infrastructures and machine learning models. But there are many limits, but the main one being the accuracy. It is known that LCA databases are quite uncertain, and it would be a great improvement to include this uncertainty into the framework. And additionally, I have shown that there is a significant offset between the total consumption of the node and what's the software-based parameter report. And I did not include that in my framework, and it will be really interesting. Of course, scope 2 and 3 are outside of the assessment. And there are changes in learning. I have focused here on centralized training when other approaches are being developed, such as federated learning, for example. That would be a relevant use case in terms of edge devices. Additionally, I have said in the beginning that training can last for days. And my methodology requires replication, so it can be very complex for those cases. And finally, I only focus on the training phase when the deployment and data collection can also have significant impacts. And I worked with a colleague to extend those last 2 points. We worked on estimating the environmental footprints of a generative AI that is called stable diffusion. And so what we did is we enlarged the scope by including the model deployment and all the infrastructure that it relies on. And so stable diffusion is an open source model, so we could replicate its training, and it is deployed online as a service, so we could have statistics on the number of users, the amount of data transferred, and the time spent on the website. Very similarly to what I showed you before, we relied on a combination of measurement and allocation from LCA databases. And so as I said in the beginning, the training was too long to replicate, so we measured only a fraction of the training, and we used linear regression from the number of steps to estimate the total training impacts. And so this graph represents the impacts, 3 impacts for all lifecycle phases and all service phases. And what we can see is that, for example, the ADP or adjunctive depression potential impact is dominated by the embodied phase of the service access or end user devices, and that the global warming and primary energy impacts mainly come from the operational phase. And finally, the deployment causes most of the impacts. So deployment including data transfer, inference, service accept, and web hosting. And we were able to publish this work at the ETSI conference, and it was also accepted. An extended version was accepted at journal. So to conclude, the impact of machine learning are booming when they should be reduced, and there is a growing need for reporting and controlling those impacts. The methodology that I use is based on LCA, applied machine learning training. It includes 3 indicators and the operational resource extraction, manufacturing, and distribution phases. And I have shown that it was insightful, versatile, and reproducible. I use this methodology to provide a multi-criteria comparison of an edge device and supercomputers. And among the key takeaway messages are that there is a significant offset between parameters, and its choice should be carefully considered. The quality target energy trade-off may be the most important metric to look at if you want to reduce the energy consumption. And in my final project, I've shown that for bigger models, electricity consumption can be estimated, and that the scope can be extended to other machine learning life-cycle phases. But this methodology could be greatly improved by increasing the scope, so adding the full node, the storage, and the network that are all necessary equipment for the node to run. And more largely in data centers, the cooling infrastructures also have a significant impact. The data collection is a machine learning lifecycle phase that is scarcely studied when there are use cases where the impact can be significant. For example, if you have data streams and models that are trained continuously, then data collection can have significant impact. Regarding the supercomputer edge comparison, I think it would be more relevant to create scenarios including both infrastructures. So you can imagine a scenario where most of the training is done on supercomputers, and the edge device only perform personalization, for example. And if we include network in the scenario, then it would provide a better understanding of the realistic use cases. Consequential LCA is an alternative approach to attributional LCA, and estimates the consequence of changing a part of the economy. And I think it's relevant in machine learning use case because there are ever-growing, ever more powerful and more specialized hardware that is designed for machine learning. And those models are put into market every few years to allow ever bigger models to be trained and developed. And however, it's more difficult to implement because it relies on marginal LCA databases that maybe are less developed. And we will need to model the relationship between key actors of the fields, like for example, GPU manufacturers or big company performing machine learning. And finally, the 3 indicators that I've assessed are not enough to evaluate the sustainability of a service. And for example, the EU AI Act is a regulation that regulates the use and development of AI, and it emphasizes beyond environmental metrics, security risk, transparency issues, and ethics considerations. And to finish on a positive note, the AFNOR, so the French Company for Standards, has published earlier this year a general framework for Google AI. And I'm happy to say that both the work that I I have mentioned today were cited by this work. So on this note, thank you for your attention.
Thank you very much for this presentation. Thank you, Mathilde. So now, good. It's okay now? Yeah. No. No.
Yes, it should work.
It should my microphone here. Yeah. Okay. Thank you very much. So we will continue now with the discussion question session. So I propose already to start. Is that okay for you?
Yeah. Do you hear me okay?
Yes.
Okay, great. Yeah, so thanks, Mathilde and your supervisor for inviting me to this jury. I really appreciated reading your document, and I'm very happy that you did your PhD on this topic that I find quite important. You did a lot of experiments. It's quite impressive all you did, and I think they are useful to the community. And so again, thank you for this. Your presentation was great. I think you illustrated it a lot. You had to go very fast to put everything, so it was sometimes not easy to see the curves because you had many things to say, but it was, I think, pretty clear and summarized very greatly your manuscript. So I have many questions. So I'm not gonna ask them all. Maybe I'll ask them another time to you if they are not answered today. I just want to come back to things that you did not mention so much today, but I wanted to, I was wondering that when reading your manuscript. If I remember correctly, you disable all the time hyper-threading and turbo boost for all your experiments, for all your measurements.
Yes.
And so I was wondering if you had any idea of the influence of this and what would happen without this disabling.
Very good question. I haven't done any study on this, but I think since training is quite, it relies on the same code. I mean, as I said, the power consumption is quite constant, and I would expect the hyperthreading to not change as well. But yeah, I haven't done any study on this, so I can't visually confirm this hypothesis.
So would you recommend to disable, you wouldn't recommend to disable those functionalities for anyone training an AI program, right?
Yeah, I think I would look into it, but for our experiment, we needed to control and make sure that the energy consumption was not influenced by other parameters than the training, so we decided to disable them.
Okay. Another thing, okay. Yeah, another question a bit on technical things. I think you, if I remember correctly, you mentioned at some point in the manuscript the GPU CPU utilization rates that you observed during the training. Did you observe any? I think you provide averages, and have you observed a lot of variations of these utilization rates during the trainings, or is it almost
I think it was
constant?
very similar to the power consumption. So in phases where the power consumption is constant, then the utilization is constant. I would say I don't have the figures. Oh, maybe I have. Maybe I will hide all the slides. How can I do this? No. So it should be here. Sorry. You know, I don't. Ah, yes, no.
Well, it's and
I
how did you? Okay.
I don't have, but I think it's very similar to the power consumption and very low, maybe on evaluation phases. I don't.
And so, when you used online tools, which
Did I took into account the utilization?
Yeah.
Yes, I think so. Yes.
Okay. So you could
divided. I think for one, so green algorithm, it includes the value inside the framework. I cannot say this was a few years ago. So, but maybe for ML impact CO2, then it doesn't ask for the value, so I didn't use it.
Yeah, I think it does not. That's why I was wondering, because it can really, well, in the end, it really has an influence on the results. And in your comparison, you don't see that much a difference. So I was wondering with MLCO2, you don't see, yeah. So that's why I was wondering which factor you put. Yeah, another question I have is on lifetime. I think you put 4 years, which is a bit optimistic for GPU probably. So why 4 years? Depends where.
I think when I was doing this, I was looking at the GPU nodes. I can't remember now the source. If that's in my manuscript, then I should definitely do that. But I think for GPU nodes, maybe the lifetime is shorter because the newest GPUs are being developed every few years. So maybe it's one of the reasons that I pushed for a smaller lifetime. I think it's around the average for GPU nodes.
And for Jetson, would it be? Do you have any idea?
I have absolutely no idea, but I wanted to use the same hypothesis so that it did not influence the results.
Yeah.
But I think it might be interesting to change those values and how they affect the results, especially that for example, the abiotic depletion potential is mostly impacted by this value. So it might be interesting to increase the lifetime of the jets.
And so, as there are a lot of improvements, especially right now in GPU, that becomes more and more efficient all the time, do you think it's always relevant? It would be always relevant to increase the lifetime as much as possible, or to find a trade-off between efficiency and lifetime? It's a tricky question.
When increasing the lifetime, it's people allowed for more trainings to be done on the same resources. So it's maybe in one word, in one scenario, it means that there are less infrastructure that are developed. But I think we can't predict how it can affect the economy, so it's hard to see how it might influence the larger scale. And there is another thing to take into account is the fact that the efficiency might be affected by the lifetime. So if we increase the lifetime, then the efficiency starts to reduce, and we need to take that into account to assess this. I think I already mentioned this. That's what I can say.
Okay. So, okay, another tricky question. I have many tricky questions with no real answers. I know. You show sometimes the quality targets against the consumption somewhere. I don't remember the slide. Yeah. So how would you? Yeah, there. How would you? Well, do you think there are applications for which we should try to reach all the time the best accuracy? I'm thinking about people often talk about medical applications, or should we? How can we decide between accuracy and consumption in the end? I think it's always good to say, okay.
That because I actually studies on segmentation of medical images, and one analysis that we did is we compared the accuracy of the model to human, to the accuracy of the doctors on the same images, and I think it was shown that yes, most of the time the human is not that great, especially on very specialized data. And then, does it make sense to increase the quality targets, because the model is trained on labeled data, so it's I mean, if we increase the quality, does not necessarily mean that the quality of the model is better. I don't know if that's clear. But yeah, I guess it depends on the use case, which accuracy is most relevant. Makes sense.
Yeah, it does make sense.
But yeah, here we can set for, like, for example, Mathilde and there, yeah. Did I put the names? Oh no, for BERT and DLRM, like you could decrease it by a very small percentage with drastically reducing energy consumption. So for those use cases, maybe we could just look at the energy, and when we detect that the learning is getting slower and slower, maybe that's when we should stop the training and think about better way to do training. Maybe a better model.
Yeah. Okay. Another thing I was wondering also with all this work on estimation is that now we use more and more virtualization processes, and I don't know how it works, all those measurements with virtualization. Do you have any explanation on that?
I think I didn't understand the beginning, so can you repeat, please?
Well, when you use virtualization, does it work the same way? I mean, like if can I measure the same way if I use like Google Colab or another tool like that, let's say, for instance? Does it measure the same way? What do I measure? How do I know what I'm measuring, the usage factor? What do I do? If I don't have really access, if I don't know exactly, okay, let's say it another way. If I don't have my node for myself, if I'm sharing, if I'm really using
Not sure I can answer that.
Okay.
Yeah, because I made sure that I was the only one using the node each time that I did experiments, especially to avoid those kind of difficulties. I wouldn't know. Yeah.
Okay, I've asked to ask a last question, so I'm going to do my last question. Okay. My last question is a more tricky one. And it's really something that's bothering me sometimes. How much is it necessary, or it's not how much, but is it always a good thing to quantify, and is it always useful to quantify? It's really according to you, it's really your opinion. There is no really easy answer, but how much do you think it's always relevant to quantify? Should we quantify everything? And yeah. I don't know if the question is it makes sense, but I don't know if you think about that already. And
I think it sounds very complex to measure everything. But I don't know. I haven't been on the real use case application, so I wouldn't know how hard it is to measure everything. But I think I do think that everything should be transparent. That we should know as at least as user, we should know what are the impacts of the services that we use. But that doesn't necessarily mean that we need to measure everything. As I said, I could estimate the total training based on the first few training steps. So it means that when you're developing a machine learning models, you have a very good idea of its total consumption. So without measuring everything, you can quantify, but your question was on quantifying, not measuring. So, yeah, I think from my point of view, it's interesting to quantify everything, at least to know, at least to know what you are dealing with. But...
Okay. Thanks. Thank you for your answer. So,
thank you.
Thank you very much for the questions. So now I will propose no.
Okay.
I don't know if it's okay.
I don't know if you can hear me if I'm speaking like this.
Yep. Yeah, I can hear. Can you hear me okay?
Okay.
Yes, fine.
So, well, first I want to thank you and the supervisor for inviting me to your events, because I've been lucky enough to be able to follow your work from nearly the beginning of your PhD.
Yeah.
So I'm very, very happy to take part in your events today. And I also wanted to thank you for all the quality of your manuscript, because it was very easy to read and it was both like precise and straightforward, so it was very nice. And as already mentioned, there was a lot of experiments done, and well, a lot of quantity of experiments and quality of experiments, so it was very nice to read. So I'm gonna ask a few questions, even though we've already discussed a lot about your work, so I don't have that many questions, but okay. The first thing I wanted to know was, have you considered using this, because you mentioned that you used only public databases for LCA, and actually just one.
Yes.
And I wanted to know, have you considered just testing other databases just to see if there is a very huge difference between the results that you got with other databases, even though they're not public, so it's not possible to, it's not reproducible, okay, but just to see if the results were significantly different?
Yeah, I have considered it, but it was not in the priority
Yes.
of things that I wanted to do. And in timeline-wise, adding the environmental impact was really towards the end of my PhD. I think I started maybe in March this year, and I was able to do that because of my collaboration with Adrien. So I mainly used the work that he did for stable diffusion. And yeah, I'm really not an expert in LSA databases. I wish I was. But yeah, I think I've been on several conferences where people were saying that LSA databases were very uncertain, and especially one was comparing two of them and was seeing huge differences. So I think it would be very relevant to include that, especially that there is no project carbon footprint on GPUs. And so, yeah,
just to see if your results are robust to the change of database. Yeah. And since you mentioned what you're modeling of the GPUs, I was wondering, because you mentioned that the memory part was most significant, and I was wondering, do you think it is really the case, or is it like an artifact of your modeling? Because since it's taking like part of it depends on the surface of your memory, do you think this is something, a real environmental impact, or do you think it's just due to the modeling that you do?
I think for mine, let me go back to my slides.
I'm asking because we had the same questions with Clément.
Yeah,
we didn't find the same modeling, so
so this
if you have an answer, I'm happy to know it.
Yeah, Okay, so the thing that I can mention is that the methodology, the assessment we use for the GPU is based on a methodology designed for CPUs. So can we say that the assessment for CPUs is robust? I don't know. But maybe in this graph here, it is represented by the RAM. That's the memory of the GPU. So can we assume that it's more robust for RAM? Maybe, I don't know. But yeah, I would assume that this data is more accurate than the one for GPUs.
Okay.
That's what
And did you compare your results with the ones for like more standard GPUs from like you know the LCA that was done comparing
which one?
The desktop computers with
I just the value we got was very similar to the one, for example, you used for Bloom, so it was reassuring.
Yeah, which was
It was not a very good assumption. I mean, based on a lot of scientific, but still it's on the same magnitude.
yeah, I agree. The order of magnitude it's okay, but okay. So we should just compare because in like Louis' work, it's really based on the decomposition of the GPU card.
Yeah.
With on a real LCA modeling, that's why I'm so like, even if it's very different graphics cards, so I don't.
Yeah,
but,
well, I haven't done that.
Okay. So I also wondered because for the comparison between HPC devices and Jetson, you mentioned, for example, that edge computing would be an opportunity to constrain the computations, and conversely, like having huge resources may encourage users not to limit their computations. Do you think this is something? So of course, it's not something that you can model in your in an attribution LCA, but do you think this is something you should take into account? Because I feel like by taking just a picture of what is currently existing is very restrictive to compare both data.
I'm not sure I understood.
Because you're not including like the evolution, well, the changes in the user behaviors that may occur because I don't know if they have access to huge HPC resources, they may launch computations for days and don't bother. So it's an open question because I don't think anyone has the answer to that.
But I think on the other way around, if there are unlimited access to edge devices, then even if there are limited access, it makes access to the user easier to be able to use edge devices. So it means that probably there's going to be a rebound effect. I don't know if that's a question.
Yeah, I'm not sure. I was wondering whether you had thought of methodology to include that, but
no, I would like to go further into the consequential LCI approach, but I haven't had the chance to really work on it.
Okay. And in the same line as Wally's question about the lifetime of equipment, yes, I was mentioning in my report that, for example, if you have longer lifetime for the servers, for example, users may start using them less and less because they won't be as efficient as the efficient.
So for edge devices?
No, for everything actually. Well, I was mostly thinking of HPC devices because I think it's more relevant for that. So it's kind of in the same line of questions that is the fact that the users may change their behavior may completely change the results too, because you will have different occupation rates of your devices, etc. So Well, for
okay, so
example,
it
that's
will
something we
influence
do on
the
Jontek
utilization.
because the older GPU generations are not used
Yeah.
as often.
Yeah,
as much.
it's the case, even
Yes.
though
So,
probably they are as efficient as.
so even if you extend the lifetime, there
I see
will be
what you
changes in the user behavior that will change your results actually.
Okay. So there is no lever to reduce the impact.
Well, there will not be research about that otherwise. It would be very sad.
Yeah, I understand what you're saying, and I'm sure, yeah, you're completely right. Because they're producing new GPUs every few years, so the old ones are maybe not used as much. Yeah, that's it.
Well, thanks again.
Yeah, great. Thank you very much. So now I will ask now Emma.
Yeah, so thank you so much for inviting me to be on the committee. You know, I'll echo what others have said. The presentation was fantastic. And like in the document as well, I really enjoyed reading it and I learned a lot, which is great. It's like a best case outcome, in my opinion, for being on a thesis committee. Yeah, so I had some overlapping questions. So hopefully, you know, I will be somewhat more brief. And let's see. So I will start with maybe some like a little bit lower level questions. So I was very surprised at your finding that you measured like greater power use or energy use from, well, power use from the Jetson than the reported TDP of 30 watts. It looked like you're measuring like pretty consistently about 40 watts. So this is actually like in contrast with some recent work and maybe also your finding that we have been doing, sort of looking at sort of Apollo style energy use in data centers, where we've been finding fairly consistently that the actual energy use is more per node, like for the GPU, is more like 70% of the TDP, of the manufacturer's sort of TDP, which is interesting, as you know, because like actually many people are estimating the energy use of these systems, just sort of like using their TDP because they're not doing like the fantastic lower level analysis that you're doing. Yeah. So why do you think that there's this difference with the edge device? Like, what do you think contributes to that?
Yeah, thank you. Thank you for your question, because I have a slide. So something that I haven't mentioned is that so for the Jetson, we started working on the development kits. So we had access to the node, and we could use a power meter to measure its actual consumption. And so it's what we can see on the graph on the right. So you can see that for this case, the total consumption is 30 watts. So we were quite reassured that the Jetson was functioning as planned. But then we moved on to maybe data center node, that we can call that, in the Grid 5000 platform. And when we noticed that there were almost a 30 watts power consumption, we were really surprised. And I don't have an explanation. Maybe there are differences between the development kits and what they sell as server nodes. There's an additional thing that I've noticed when working on the cluster is that okay, so I've seen how it was organized. The Jetsons, you know, the very little boxes, they were placed alongside each other. And that means that they were influenced by the temperature, especially when all the nodes are working together. They consume more power individually than when only one of them is working. So I'm assuming that maybe it influences the consumption here, but I would still say that it's mainly from the difference between the development kit and the server node.
But they don't, is there not, but yeah, NVIDIA doesn't report like a higher TDP for the two, for like, yeah.
I was really surprised. It would require more investigations on this point, because on like the specification, it was exactly the same. And I could access, you know, there is a power there are power modes. There's 10 watts, 20 watts, and 30 watts. And on this case, it was not working. Like if I would ask for 10 watts, then it would consume the same. So I'm assuming there is an issue here. But I would still say that we need to be very careful because I've noticed that, the relationship between the actual consumption and the TDP was very unreliable. And maybe, sorry.
No, yeah. I mean, I think either way, this is very good to know because I would imagine, moving forward, folks, want to make estimates and they, ideally, it's hard for everyone to have access to do like sort of low level measurements that you're doing here. And like, if they went off of like our statistics that are saying sort of for server hardware, it's usually about 70% the actual energy use compared to TDP, then they would be wrong if they want to sort of extend those analyses to edge devices separately from like understanding exactly what's going on here. So this is really interesting. Okay, so another question about the utilization, or actually, sorry, the power consumption. So the sort of spikiness throughout training of the power consumption, can you explain like sort of like what those spikes are?
It mainly comes from the evaluation phases. It's sort of like I haven't been very specific about this. But yeah, you have a training step and then it is followed by evaluation phase. So you can see the evolution of the accuracy on the train and test data sets. And I think it directly corresponds to this. I'm sad because I didn't include the one with the details per CPU and GPUs. But if we look at the power consumed by the CPUs, it actually increased during those phases. So maybe it's also processing the data and making it go to the GPU. And it's at different intervals because the models trainings are configured differently. And I think, for example, if we look at R and N, maybe the transfer of data is actually influencing the training, and it would be interesting to look at other way of transferring the data because it seems like it's affecting the training. And actually, I think it was for ResNet, we were first using the online storage. I don't remember the real name, and we noticed that it influenced greatly the training time. So we moved the data locally, and that's the results were much better.
Does I'm trying to remember, does MLPerf specify the sort of like frequency of evaluation?
That's a very good question. I don't know. I wouldn't know. But I guess it's up to the developers because I mean, if you miss the point where you reach the quality target, then maybe you're having a longer experimentation. So it's part of the hyperparameter search to select the best frequency for evaluation. But I don't know if it's given by the benchmark.
Do you think that it should be? Like, I guess, yeah. And so, yeah, do you think that do you think that the evaluation frequency or other parameters around, because it does, right? It's impacting the sort of like overall energy use in a way. And like, so do you think that it should be sort of included in these measurements? Or yeah, what would you recommend?
It depends on the infrastructure and the batch size that is set by the computing nodes. Like if you have 2 nodes or 16 nodes, then the frequency would be different because I mean the learning would be faster. So does it make sense to set one frequency for everything? Yeah. So in conclusion, I don't think it should be. But yeah, maybe those graphs are not the most representative of the benchmark because I manually set it quite low. So I could have those nice graphs that I've shown before, that we could see the evolution of the energy.
Yep. I mean, definitely makes sense. It's a trade-off we have to, deal with. I was interested to know what your thoughts were on it. Okay, so maybe a little bit higher level of a question. So in terms of thinking about the trade-offs and differences between sort of data center energy use and energy use on edge devices, I think characterizing and understanding like inference or use is actually like really interesting. So yeah, I mean, probably we think that inference makes up actually like a larger proportion of overall energy use due to AI, and probably that'll only increase moving forward. And so I was wondering if you could, I know you had, you know, in the sort of future work section, you discussed some work that you've already done, sort of like characterizing the deployment inference phase. But I was wondering if you could speak more to you know, are there sort of some unique challenges to extending this analysis to inference? Yeah, what makes it different? What makes it hard? What makes it easy? How would you do this for understanding inference?
Okay. So inference is characterized by the fact that it requires less computation than training, right? So it means that you need to adapt the infrastructure for inference. But how can it impact? I think you know, measurement-wise, it would be quite similar. But there is one thing that we have discussed in the last project that I presented, is that we don't know how we can parallelize inferences. Because what we did is we measured like 4 inferences, but we don't know if we could concatenate inference to and just improving the energy efficiency. That's, yeah. The thing is, the issue that we had and that we need to have, what we want is to evaluate the impact of inference, is that we need to know the number of users, or we need to have access to the nodes. So if you have access to the node, then it's pretty easy. You can measure everything, and you also know the number of requests, so you can maybe allocate the impact to the inferences. But if you don't have access to that, then it's more complex. And what we did is actually an estimation, because we don't know if they are able to handle a large number of requests or not. We just measured for 4 instances, I think, or 8. But yeah, but yeah, I think for inference, I think edge devices are really designed for inference, so it would be really interesting to add that in my analysis. That's true. Because I don't know, I have this assumption, I don't know if it's verified, that if you use the device at its maximum utilization, then you also maximize its energy efficiency. I don't know if it's a good assumption. So if you use like very large machine learning nodes for only one inference, then on my opinion, it's under dimensioned. And I mean, it would be really interesting to do the experiments, but I think you would lose energy efficiency. And in those scenarios, maybe edge devices can help reduce the footprint.
So if you, I agree. Like, I want someone to do this study, because I think it'd be very interesting. Maybe you. So if you did want to try to, so let's say you didn't have access to the nodes and you did want to try to simulate, simulate a set of users, sort of pre-model, like what would be the like variables or parameters that you would sort of maybe need to vary, like for each user, or just, yeah.
So if we start from our use case of generating images, we add a lot of parameters to sets, like the size of the images and the number of images simultaneously processed. But yeah, more generally, one user is doing one inference, and then the number of the parameters that would be relevant would be just the number of users, the data that is transferred, and the number of inference per users. What else? Maybe, yeah, so the data transferred and how long maybe users are using the services. Because in my last graph, I have shown that the user devices represent most of the facts. So it means that the time during which the users are connected is a significant parameter to take into account.
What about, so for edge devices, and if you're looking at like emissions in particular, and for edge devices, are there any other factors you would need to take into account?
So it depends if you consider that the edge device is shared or not, right? Then if it's not shared, you need to define the, I don't know, the interval at which the device is used and the time at which it's idle. So yeah, you need to take that into account. And if it's shared, then it's the same parameters as server node. Does that make sense?
Yeah. Potentially like the location of the device too is a really interesting factor, right? Because that can, you have much less control over where energy is coming from and the sort of carbon intensity in this sort of distributed setting, particularly for inference where, it's going to happen when it's going to happen, where it's going to happen, basically. Okay, so I'll wrap up with one last sort of high-level question. So what are like the couple of key takeaways for policymakers, for example, for this work? So like folks working on the, who worked on the EU AI Act, or who are working on sort of like putting that into motion.
I think the most important one is that there is a huge offset between software-based, what I call software-based parameters and the actual consumption of the nodes. Because if you don't take into account everything, then you would lose maybe 20–25% of the actual consumption. So I do think that policymakers should take this into account to make sure that everything is reported accurately. Then, as I said in the beginning, I don't think it's maybe very important that everything is measured all the time. But if you know all of the parameters, like the training time or the number of training steps, you can rely on only measurement of one steps. But mainly those 2 points.
Cool. Thank you so much.
Yeah, thank you.
Right. Thank you very much. So now I propose Claude de Lapo.
I'd like to thank as well for inviting me to this jury on very interesting and important topic. And also I'd like to repeat the fact that the manuscript is really well readable, well written, easy to follow. And you see clearly what you have done, what you decided not to do, and so on. So this is great. I will have just one question, but I believe that it's a difficult one, which is the following. Each time we do that sort of exercise, we look at things very globally. What is the number of kilowatt hours? What is the carbon footprint by multiplying? I don't know, it depends how you do it. What is the material that is there? And in fact, if you really back up, and take an environmental posture, things can be depending really on where you are locally. So in terms of materials, maybe not, because we have a global market and so on. So maybe it's an approximation that it's fine. For electricity, it's already it can already be discussed. If you go from electricity to carbon footprint, then it really depends where you are and whether some electricity has been produced from gas, coal in the region where you are. And when we come, it was not part of your PhD, but when we come to something like water, it becomes a little more local again, and can really be a problem. And if a data center starts using a huge percentage of the water that is available in summary, it's a problem. So I'd like to know if you have been thinking of that, and if you have ideas on how we could take into account the fact that there are local impacts to be looked at, and not only the global figures.
I made sure that I did not include in any of those research topics in my PhD because it's a very complex one. Yeah, I do think for machine learning it might be very relevant to look at those issues, because training is usually not dependent on time or location. So if you plan on doing a very significant training, then it's completely relevant to look at where you do it and when you do it. But for the edge devices, it's much more complex because you don't control where the user are. So yeah, so you don't. I mean, it would have been very really hard for me to do this estimation. But I think it's a super cool perspective because those parameters really, I mean, there are parameters that I selected, and it would be really relevant to do a sensitivity analysis on how the impact factor of electricity influences the total values of the trainings. But it's a really large research topic, and it's nowhere computing volume. And I think it would be relevant to include those for machine learning use cases.
So the second step of my question, do you believe we can take your methodology and combine it with something else to reach our goal?
Yeah. And I did a very small sensitivity presentation. I included lifetime and the active utilization rates. But we could definitely do the same with the impact of electricity. And, yeah.
Thank you.
Thank you very much. So we have
Thank you very much. I would like to first to join to the global praise for your work. Both the documents and the defense. So that was also pretty fantastic, as was already said many times. And thank you very much for inviting me. I'm very honored to be there today, especially for this topic, which I find especially interesting. I had some question about water footprint, but I won't ask it.
We can discuss it afterwards.
Okay. Some question about the functional units.
Yeah.
Especially about the quality targets, which was already, I think, mentioned by already. For me, it looks a bit like arbitrary, and in particular, it seems that it depends on the data sets. I mean, if you choose another data set, for instance, for image recognition and things like that, if you change your data sets, then you will not be able to reach the same quality target. However, I think your methodology strongly depends on this functional unit and on the targets. How can you help, I don't know, people, policymakers or developers to the right one?
So I think the definition in ACA, the ESA technique is that it needs to represent the expected performance for the end user. So I think it would not make sense to use a smaller one, something that would not be used. But here, I think it was said so that the computing nodes would not spend too much time on this. Like, for example, maximum 40 minutes maybe for the benchmark, so that it will not require too much resources for the companies that wanted to include their clusters into the benchmark. But, it needs to be relevant for the end application, for the application that is actually going to be deployed.
Okay, and taking a step back, still on the same question on the functional units. Here you focus on a very specific kind of algorithms, namely deep learning algorithms. If you switch to the end user point of view, for me, what's interesting is that the system is able to recognize images correctly or things like that. Actually, I don't care the actual algorithm which is run for that. Would it be possible to extend your methodology to other kinds of algorithms by focusing on functional units that don't include
the model?
Yeah, exactly.
Yeah, it's relevant. I hadn't thought about it, but yeah, if what you want is something that is able to classify images at a certain level, but you don't really care about which model and which data set is used, that's the relevance. And it would allow to open the door for smaller models or maybe expert model. It would be, yeah, excellent question. It could be really relevant. Yeah, I think they do so because they want to compare computing nodes. And so they don't care about other models. So yeah, I think you're right. We need to define data sets and the model for methodology at this.
Yeah. Some question has been asked by already, I think, about virtualization, or it was. Okay. Wonderful. I had a quite similar question about the shared infrastructure, not really virtualization, but just suppose that you share your infrastructure with someone else. And I was wondering whether, for instance, RAPL measures could be based on, could give you some information about the per process consumption or things like that, whether you are able to correctly discriminate between processes.
So when we were writing the first paper on software-based parameters, we discussed about this because my colleague was focusing on CPU and virtualization, virtualization, and he had this criteria as differentiating software parameters, but none of the GPU, none of the software that included GPUs had this functionality. So the most simple way of differentiating is to use the utilization of each users. But I think it was shown that it was not a very good way to share the power. But I don't know if it would be interesting in terms of machine learning approach. So the question was.
Whether you can use your methodology to extend to a shared infrastructure where you discriminate between the different processes and use the same nodes.
Yeah, you will have to define how you allocate each workload. Yes, the most simple one is to use utilization, but it doesn't sound. I don't think it's it's the most simple one, but I think it will require more research. I don't think we've reached. It's easy to allocate. There is this idle power consumed by the node, and I think it's not clear if you use utilization, if this node is fairly shared between users.
I don't know. Maybe I'm better specific.
But yeah, it's not an easy way to do that.
Yeah. And a very last question, that's an open question. Really, not very nice. Okay, so just to have your opinion. So your objective with this thesis, one of your objectives is to provide ways for policymakers to act and to reduce their footprint.
Yeah.
What can you do when you see that the trends, the global trends that you show at the beginning of your document on your presentation are exponential? I mean, the number of floating point operations dedicated to training those huge models are evolving exponentially. So, what do you think?
An influence.
Yeah, how does the methodology influence?
Well, the
That's a
regulations.
messy one, but
Yeah, regulations. I think is the main lever.
yes.
I don't know. I think when I started my PhD, I wanted just. I personally was curious about the impact of the uses that I did, and I didn't know. So I think I think it would be. I think at least at this point, I think being transparent on our impact, or the impact of the digital services that we daily use should be. Maybe that's good an influence on the user parts, but I think it doesn't. I mean, everything is decided by the companies that train larger models. I think the user really has an influence of that. So the regulations. Yeah, that's the answer.
Thank you very much.
Great. Thank you, Tita. Laurent?
Yes, merci. Thank you, Mathilde, for this very nice scientific journal. It was really a pleasure to work with you. You managed to be at the same time in Lyon and Grenoble. I don't know how you did it. I know in Lyon maybe it was not so easy. You were the only PhD girl in the team with all these boys. So tell me once how it was. I know it was not easy maybe. I was very impressed by how you manage the collaboration during your PhD with HP, by going on supercomputing with 5000, by going on Jetson and Edge. I don't know how to say that in English, but you have galéré a lot. Yes. And also the collaboration you had with the other PhD students like Adrien and Vladimir, that was very nice. I really enjoyed that. I also discovered two of your artistic skills that I didn't know before. Unfortunately, it's streamed on YouTube, so I can choose the video, but in terms of dancing and singing, that's very nice. Okay, it was impressive. I also want to thank Denis for inviting me on this co-advising of Mathilde. It was a long dream for me to discover the Tristram method advising, which is a mix of positivity, performance, and sufficiency. I could design that. And it was great to work with you all three together. It was a good pleasure.
Okay.
I wish you a nice world discovery in the next month.
Thank you.
So we are almost done. So let's start by thanking all the members of the committee for their nice participation and many questions that are very relevant, actually. We are working on some of them. Yeah. We can elaborate later. And it was also a great pleasure to work with you, Mathilde and Laurent, and very comfortable to rely on you, Laurent, because I'm known as a theoretician, so many parts rely on your skills. And we are actually, you manage your time very efficiently. So between Lyon and Grenoble, and we had meetings every week during this full duration. And okay, about the scientific side, maybe I want to paraphrase your conclusion somehow. We started with you, actually, the major topic within my research program at the BI Institute, because it was somehow important to, as a language with the other researchers, just to alert them, well, okay, it costs a lot and you have to experiment this. And now this is one of the three pillars actually of the new research program, which will be handled by Tom here. And as you said, this is how to report and to make tools for estimating or actual measures with Guillaume. So it was very nice to see that after this PhD, we are there with a good, clear view. And we can use this for helping with decision makers, but also colleagues that should be convinced not to exactly like Sigma record. So we cannot use deep learning everywhere. And measure is one of these way to alert them somehow. Probably not so efficient. Okay, I have a few questions, but I will have you later on the edge and extreme edge because later. Thank you again.
Right, thank you very much, Denis. So I will not ask questions because for your information, you had around 35 questions. Okay, so I think it's enough. I will have some, but I ask you offline. Okay, so thank you very much. So we have. We will
stay here.
We stay here.
Yes, we just stay connected,
okay.
Emma and